A critical engine is the engine that, if it fails, would cause the most adverse effects to control and performance. In other words, we don't want either engine to fail, but we really don't want the critical engine to fail. With most North American twin engine aircraft, the critical engine is the one on the left. This is because most North American twin engine aircraft have the conventional design, with both propellers rotating clockwise from the pilot's perspective. And this causes some important aerodynamic effects concerning engine failures. To help understand and remember why this is, a helpful acronym to use is PAST: P factor, accelerated airflow, slipstream, and torque. P factor, or asymmetric thrust, is a propeller effect where the downgoing blade has a higher angle of attack compared to the upgoing blade. And this difference is less significant in straight and level flight, where the aircraft's angle of attack is lower, and more significant when the aircraft has a higher angle of attack. So, because the downgoing blade has a higher angle of attack, it takes a larger bite out of the air and creates more thrust than the upgoing blades. So, this asymmetric thrust in a single engine aircraft creates left yaw. The same thing happens with a twin engine. However, when we look at where these forces are acting through on a twin engine aircraft, we can see that the extra thrust created by the downgoing blades on both engines are at different distances from the center of the aircraft. The arm is greater for the thrust being produced by the right engine, which means it has a greater moment, a greater rotational force being applied to the aircraft's center of gravity. So if the left engine fails, there will be more rotational force coming from the right engine, requiring more opposite rudder correction. If the right engine fails, there would be comparatively less rotational force coming from the left engine, requiring comparatively less opposite rudder correction. So between the two, it would be worse if the left engine fails. And that's why the left engine is the critical engine. Each engine mounted on the wing produces extra airflow around the wing. This extra airflow means more lift. And as we know, there is more thrust being produced by the downgoing blades. So there is greater lift in these areas. Once again, the extra lift created by the right engine is farther away from the center of the aircraft. It has a greater arm. Greater arm means greater rotational force. So if the left engine fails, there is no more accelerated airflow from the left engine. And the accelerated airflow from the right engine with the greater arm amplifies the roll, more so than if the right engine fails, since the arm is shorter for the accelerated flow coming from the left engine. Once again, you can see how the left engine is the critical one. In normal flight, with both engines working, the spiraling slipstream looks something like this. Why are both slipstreams moving to the right? It's because the extra thrust created by the downgoing blades means faster moving air. Faster moving air means lower pressure. And as high pressure air always moves towards low pressure air, the direction of the slipstream moves off to the right. With this in mind, the left engine's slipstream makes its way to the tail section, and two things happen. It hits the tail from the left, pushing the tail to the right, resulting in a left yaw. And it's also supplying extra airflow around the vertical stabilizer, which allows for more rudder authority. When the right engine fails, that slipstream airflow wasn't affecting the vertical stabilizer in the first place, so not much changes in that respect. But the left engine is still running, so it's still supplying that extra airflow to the vertical stabilizer, and it's also pushing it to the right, which actually helps with compensating for the right yaw that results from a right engine failure. If the left engine fails, that slipstream is gone. So, while the left yaw associated with the airflow hitting the vertical stabilizer from the left is eliminated, so is the extra airflow that it also supplied, resulting in less overall rudder authority, which is not good since significant right rudder is needed in a left engine failure. So, the left engine is the critical engine. Torque is the tendency for the aircraft to roll in the opposite direction of a spinning propeller. If the right engine fails, the aircraft will yaw and bang to the right, but the torque from the left engine is actually helping counteract the right roll by trying to roll left. If the left engine fails, the aircraft yaws and rolls left. The torque from the right engine acts in the same direction, so it actually encourages the roll. All of these things acting together makes it much less desirable for the left engine to fail. And that is why the left engine is the critical engine. Now, of course, there are counter rotating propeller designs, which eliminates these problems. So, an aircraft with counter rotating propellers doesn't have a critical engine. So, why aren't all twins made this way? Doing so adds expense and complexity. So, the conventional design with both props rotating clockwise are far more common in North America.